So, very good evening to all members gathered here. Now we are in the next session, number 5, design of shaft from the course design of machine elements. We will see what are the main things we are going to discuss under this topic. First, let us discuss the overview of the topic headline, design of shaft. So, what do you mean by a shaft? It is a round cylindrical object. So, it is commonly present in industrial machineries. The main function of the shaft is to transmit the mechanical power and torque through combined rotary motion. So, normally shaft is found in lathe machine, milling machine, any industrial basic production machineries, we can able to see the shaft element. Here, what are the various the design aspects in shaft we are going to discuss? That is the major theme of the presentation. So normally, the shaft has to withstand the stresses due to torque, bending moment, and also the axial load. So the most critical aspect of mechanical design is affecting the overall machine performance and lifespan. If a designer makes a wrong dimensions of shaft, so that will not serve the purpose. So it will affect the overall performance of the machinery and also the lifespan usage time. So you have to carefully consider the different design parameters while designing the shaft. What are the key consideration in shaft design? Material selection. Normally, carbon steel material is widely used for the strength and better machinability, while alloy steels are preferred for high strength needs and requirements. Next one is strength. Shaft must be highly strong enough to resist both static and dynamic stress. So it requires to have adequate factor of safety. The next one is material rigidity. Shafts need high sufficient rigidity to prevent excessive torsion and lateral deflection when it is under dynamic condition. Thereby, we can avoid resonance due to vibration and unwanted critical speeds. Then, depending on the loading types, shaft design must be considered following loads like torque, bending, moment, or combined torsion and bending loads, as well as axial loads in some cases. Then, design criteria, deflection, frequency response, fatigue life, and manufacturing limitations. These are the main design criteria which will strongly influence the shaft dimensions and tolerances. Then stress analysis. Methods like distortion energy theory of failure mainly used to analyze the stress on the shaft under various loading conditions. So bearing consideration. The relationship between the shaft housing and bearing design must be carefully considered in order to have a proper fit and minimize the wear. The shaft is being supported by two fixed grip end that is called a bearing. So the bearing support should be highly rigid enough and it must have a comfort fit by minimizing the surface wear. What are the various types of shaft? So as per the classification, which is given here, each type has a specific point of area of usage. Now let us see the general design process and shaft design. First thing, We have to identify the load estimation. How much torque the shaft will be withstanding bending moment and any axial loads acting on the shaft. Calculate the stress like shear bending at a critical speed and select the material with a better appropriate strength and other properties to be considered while designing. Determine the dimensions. Say, calculate the necessary diameter and other dimensions based on the safe stress limits. Consider the features like keyway, coupling, and bearing seats in the design. Analyze the deflection and critical speed. Ensure whether the shaft meets the deflection requirements and avoids vibration due to resonance. Now let us see a practical illustration example under design of shaft. In this problem, we are going to find out only the diameter of the shaft, cylindrical diameter of the shaft. What are the supporting informations are given in the problem statement? Let us go through it once. Consider a commercial steel shaft which is used for machinery application, which has a lever mechanism. And shaft is supported at two ends, A and B, as shown in the figure. So you can able to see the point A and point B. This is point A and this is point B. And this one is C and point D. There are totally four nodal points in the cylindrical shaft. A and B is the fixed bearing support which is acting at the left and right side of the shaft assembly. The shaft carries a lever and the counterweight. Both are keyed to the shaft at point C and D respectively. A rope which is attached to the end of the lever, which is at a distance of 20 mm away from the shaft axis. This rope is begun to pull down due to its motion, downward motion. As a result, the rotary motion of the shaft is little bit resisted by the counterweight W measured in Newton. So we don't know what is the value of the counterweight W. That also we have to calculate. But the distance of the counterweight is 60 mm on the opposite side of the lever, as shown in the figure. You can able to note here the distance of the counterweight. Calculate the value of the counterweight W and design the shaft if the allowable shear stress of the shaft material tau is equal to 55 Newton per mm square. So we want to calculate the counterweight and also the diameter of the shaft, two things. So the given data, so the force acting on the rope from the figure it is given 7 kilonewton, the vertical downward force due to pulling effect. So convert the kilonewton into Newton by multiplying 1000, 7000 Newton. So this is the shear stress value from the given data, 55 Newton per mm square. Now we will see the solution part. So the load 7 kilonewton applied to the lever at a distance of 20 mm. So it produces a torque due to twisting moment. So calculate the torque acting on the shaft. So the formula is torque equal to force into distance. So 7 kilonewton, that is 7000 Newton into the distance of the lever 20 mm away from the shaft axis from the given figure diagram. So you can say here 7 kilonewton into the corresponding distance. The torque acting at a distance of 20 mm with the allowable vertical downward force 7 kilonewton. So multiply those two values and find out what is the torque produced at the shaft due to twisting moment. And this value is used for calculating the counterweight also, right? So we know that the applied torque equal to unknown weight W into distance of the unknown weight from the given figure is 60 mm. So W into at how much distance the W is placed? 60 mm. So calculate the value of W, the counterweight in terms of Newton. Now we have two loads at point C and D. One is the counterweight, the other one is the weight due to the rope which is keyed on the lever. So there are two loads acting downward at point C and D respectively. Now let us find out the bending moment using the bending moment load diagram. So before that, assume this shaft as simply supported beam. Draw the free body diagram and followed by that, calculate the support reaction force at A and B, and finally draw the map for the bending moment load diagram. So first thing is, consider the shaft as a simply supported beam. Both the points are fixed A and B. RA and RB are the unknown reaction forces acting at the fixed end, and these unknown reaction forces are facing in upward direction, so it is considered to be positive. Now take the moment about the point A. The sum of the moment acting at a point A will be brought to zero. This is the assumption. So based on that, calculate the RB value, reaction force at B. Now we know the equilibrium condition. Sum of the reaction force is equal to the point load which is acting at the point C and D. From that you find out the RA, the reaction force at RA. Now we have two reaction forces, RA and RB. Okay, now it is easy for us to draw the bending moment graph. So what is the bending moment at A and B? Always in a simply supported beam, the bending moment at the fixed point dead end will be zero because there is no force because both the ends are fixed. Now bending moment at C and D we have to calculate. So from C, refer towards the left side direction. There is one upward reaction force. How much distance from the C? 50 mm. So RA into 50. Similarly, bending moment at D. So from this point D, C towards right hand side. So there is another reaction force RB. The distance is 30 mm. So RB into 30. So calculate the bending moment at C and D. And out of these, which is the maximum bending moment? It is found to be at the point D. Now write that as a final value, the maximum bending moment. Now we have to find out the equivalent twisting moment, that is the combined bending moment due to torque as well as due to bending. So this is the equation for equivalent twisting moment. MT equivalent is equal to square root of MB whole square plus MT whole square. MB is nothing but moment due to bending. MT is nothing but moment due to torque. So combined torque and bending you have to consider by taking square root. So we will get the equivalent bending moment in terms of Newton mm. So using this result, find out the diameter of the shaft. That is our final ultimate path. So using the value equivalent twisting moment equal to pi by 4 into tau into dq. We know the value of tau, allowable shear stress, 55 Newton per mm square, whereas the value of dq is unknown. So we have to find out the diameter of the shaft. So it is found to be 17.45 mm. Round up to the nearest integer. So it is 18 mm. So the dimension of the shaft is 18 mm. So according to this problem. So from this, what we come to a conclusion. So we know the loads which are acting on the shaft structure, but we don't know what is the diameter required to support the loads, weights which is acting at the point C and D. So basic knowledge of statics and dynamics are applied to find out this process in a step-by-step sequential way. So from this few information, I conclude that shaft design purely relies upon optimizing for strength, high rigidity, and more fatigue life. So the following design factors like stress concentration due to bending and torque, material selection, and other manufacturing constraints, these are the most essential factors. The primary goal is to ensure that the shaft has to reliably transmit safer torque and rotational motion without having any excessive bending or deflection, either under combined loading conditions. So with this information, I once again thank all the members who are here. We will meet in the next topic, design of coupling joints from the same course, design of machine elements. Once again, I thank all the members. Thank you all.